Hi, so here is my quick take of what goes through my brain as I do a COMSOL simulation. So this is part one, which is just looking at setting it up. So the first thing is, which model should you pick? Certainly the more you move from here to here, the more time it's going to take and the less likely it is to converge. So I don't think I can do anything in 1D, so 2D is sort of the simplest I can do, so I'm going to pick that. And then my next choice is, well, is an acoustic simulation or a fluid flow simulation? Certainly not a structural mechanics or heat transfer, so we'll start with fluid flow. I can make a movie also for the acoustics one. In the acoustics one, we only have one option really, which is the pressure acoustics frequency domain case. But in this example, I'm going to do fluid flow. There's a bunch of different fluid flows. There's thin film flows, so that's water fluid going between two things close together, high Mach number flows, non-isothermal flows, all sorts of stuff, multi-phase flows if you have particles in your flow, but we're going to do a single phase flow. And we're going to do laminar flow. This is Reynolds number dependent. Turbulent flow, certainly turbulence makes noise, but we're not interested in the noise made by turbulence, and turbulence, it doesn't converge nearly as well as laminar does. So we'll go with laminar. And then we have to pick a study type. We have two options. The flow either doesn't change with time or it does change with time. In this case, the mean flow might not change with time, but the fluctuations definitely are what we care about, are important. So we have to make it a time-dependent study. Time dependence means that it's not the same now as it is 5 seconds from now. And so depending on what your cycle is of your fluctuations, you may or may not see it. So now we've got to build the model. You can actually just say I want a rectangle, and you can just click and drag it out. I don't recommend doing that. I recommend instead first defining parameters. So we can define a length is 10 centimeters, and we can define a height as 6 millimeters. Courtesy of Bethany's measurement in class. And then I can say I really want to add a rectangle of width, length, and of height. And if I build it, there it is, kind of small, so I can zoom in with this button. And now it zooms it to fit. I can see it makes sense. It's out to 0.1 meters and up to 0.006 meters. So that's all good. I'm also going to add a point. So by adding a point, I can say I want to put a point in here that I'm actually going to ask you what the pressure is doing at that point. So that might be somewhere down the tube. We can say maybe it's 95% of the length of the tube, and it's halfway up the tube. And then I can plot that, and you can see there's my point. So I can ask it to do averages over a surface, or I can say just what is the pressure at this point as a function of time, or what's the standard deviation, or whatever. Next, I have to define a material, so I can say define a material. I say everything else, I do a right button click to see what are my options. Define something from the library, type in air, and search for air, and what do you know? It was a recent material. I double click, and now it's filled my domain up with air. So the only thing it's going to solve is inside the box. The next step would be to say, okay, let's look at the flow that we have picked. So the flow we have picked is incompressible. That's not right. We need compressibility because we need the pressure and density to fluctuate, for us to get a sound wave. And we are going to neglect the Stokes flow terms. So that is, remember, it's the rho u du dx and rho v du dy terms and w du dz that we said both the fluctuating term and its derivative are small, so the product is very small. Everything else, we don't have any turbulence. We can certainly go with this reference temperature and reference pressure. That sounds fine. Fluid properties, the only thing we're going to need to add is we want the density to not be the material density, but to be the adiabatic assumption, which is the overall density. So for air, about 1.2 kilograms per meter cubed, plus the instantaneous pressure divided by the speed of sound squared. Now, if you notice, when I click on this, I get a yellow jagged line. If I do a mouse over, it says I don't know what A is. So I can go back to parameters and I can define A. A is equal to the speed of sound. I can type in 343 meters per second. Or I can actually select all of this and say here, I want to go in my model in the component 1, which is this box, from its material functions, I want the speed of sound. So CS is the speed of sound. And when I do that, you'll see I get a red line under it. And the reason I get a red line is because T is not defined. So I need to define a temperature. So let's say T is equal to 20 degrees C. And now I have 343 as my speed of sound. So that's all looking good. I've got a geometry, I've got materials, I've got initial values, I've got my fluid properties, this density that varies with speed of sound, and you'll notice that no longer do I have the yellow underline. The last thing is right now I have walls around all 4 sides. So that means that the fluid's never going to move. So we need to activate the fluid in some way. And one way is to actually have a little section of fluid in here that's slightly higher pressure. Another way is to put a hole up here and blow through it, sort of like a flute. We're just going to move the left wall. So to do that, we need to define an inlet. So I'm going to define a new inlet. You can see I can define my inlet, and I'm going to say it's this wall here. I can define it as velocity, or I can define it as pressure. We can say it's P0 times the sine of 2 times pi times F0 times T. I'm going to get rid of suppressed backflow. That is, suppressing backflow will often speed up the convergence, but I don't think it necessarily applies here. But you can see I have an error because it doesn't know what P0 is. So I got to go back to my parameters and define P0. There's a number of ways I can define P0. The easiest for me is to think about in terms of dB. So if you remember, dB is 20 log of the dB value divided by the smallest pressure you can hear, which is roughly 2 e to the minus 5 pascals. Multiply that by 10 raised to the, let's say, 50 dB divided by 20. Gives me an initial pressure, which is very small, something like 10 to the minus 2. And then I also need to do an F0. So I have to pick any frequency. If I'm going to do a parameter sweep, it doesn't really matter what frequency I pick. I'm going to go ahead and pick something that is, let's say, the speed of sound divided by 4 times the length. Because 1/4 of a wavelength can fit inside the tube and resonate at that. So this gives me a frequency of around 800 hertz. I noticed a couple of people actually did something where they said wavelength is 4 times the length, or 1/4 of a wavelength is the full length, and then said A divided by wavelength, which is kind of nice. So that's also a good solution. You get the same answer. So if we go back to our inlet now, there's no squiggly line anymore because both P0 and F0 have been defined. I can choose a mesh. For this, we can probably go with a fairly coarse mesh, so it will find an answer fairly quickly. You can build the mesh to see how coarse is coarse. That actually looks like a lot of black lines. We can zoom in if we want. And see what they've done. You can see they're trying to resolve in some degree a boundary layer and then wide steps in the middle. For the study, we need to figure out how long we're going to go and in what time step. So let's go back to our parameters and let's define a time step. So dt, and our time step is going to be, for one cycle, so 1 over f0 is the amount of time it takes to do one cycle of our frequency. So if we want to get 10 points within that cycle, we want to multiply this, or divide this by 10. So we want 1/10 of that total time per cycle, and that gives us our dt, and then our total time is going to be something like 10 cycles or 20 cycles. So 20 times 1 over f0. Again, I noticed a couple people did time per cycle and said that's 1 over f0. And then you can do The dt is 1/10 of the cycle time. And this is equal to 20 times the cycle time, so 20 cycles, which is kind of nice because it makes it a little more legible. So I have that. If I go back to my study, I can say I want to do a range starting at 0, going in steps of dt, and go to total time at the end. And oops, you can see it likes that. We can go ahead and hit compute because everything should be ready to go.